So, in this video, I'm going to talk about the real-world circuit design problems you can't solve without programming. So, first off, why do electrical engineers need to know code? So, in modern fabs, electrical engineers simulate, verify, and optimize circuits using code. Here's how C++, Python, System C, and Verilog are essential in AI semiconductor design. So Verilog gets used for hardware description, like designing actual logic circuits for AI accelerators like TPUs or NPUs. And then C and C++ are used for hardware-aware algorithm prototyping and embedded systems programming. You use Python for automation, modeling, and analyzing data from chip testing and validation. Python is used for testing basically and modeling the chips. You use System C and system level simulation and architectural modeling in fabs. And coding is tied directly to the performance, power, and manufacturability metrics. So here we present like a problem, and then we arrive at the conclusion that why you need to know coding basically to solve this problem. The problem itself is about managing logic synthesis. Here's a brief description of the problem. So, some background stuff. Some AI circuits have millions of logic gates, but converting human written logic into silicon causes bottlenecks. And the question is, how do we manage logic synthesis for performance and power? So now we're going to look deeper into the problem. So AI chips often fail timing due to poorly optimized logic paths. So the designers write RTL in Verilog, but synthesis tools may generate inefficient gate level implementations. And this leads to another problem where there's too much power usage, there's increased area, and critical path violations in high frequency AI workloads. This, in fact, leads to multiple problems. So, we're now going to try to arrive at a possible solution. Here's one possible solution that we thought of. So, what about changing the tools used for synthesis and changing the logic that is used? Would this be a solution to the problem? So, we arrived at the conclusion that switching synthesis tools may help, but they all rely on proper coding techniques. And the big thing here is there are a lot of constraints. That's the challenge. There are a lot of constraints with switching synthesis tools. So that's a problem. Gradually changing logic becomes impossible at the complexity of AI. AI is made of billions of transistors. And this leads to a problem because this leads to not being able to tell the difference between interdependencies within logic blocks, which are only captured through simulation and automated tuning. So we then finally arrived at the ultimate solution. This solution is a combination of three coding languages: Verilog, TCL, and Python. And it also allows engineers to have control over logic flow, timing, and electrical constraints. Here's the solution itself. So use Verilog for RTL coding, add TCL constraints to guide synthesis. Synthesis refers to the time targets, area, and path groupings. Also want to script automated design space exploration using Python. And I use Python for this. And you do that to analyze the outputs. The outputs are the timing reports, power, and leakage in this case. And then once you've done that, you want to check this and test it. So I'm going to validate this with System C and C++. It's co-simulation of the hardware architecture. And the reason why this problem works and what it does is it makes it easier for electrical engineers to code maps of silicon. It makes it easier to have control to code maps to silicon. And another thing that it does is it also speeds up verification. This allows for high-speed simulation of workloads like matrix multiplication and AI. And it also connects design with the actual chip. So we have arrived at the conclusion that this is the ultimate solution to the problem. So that is all for today's video.